Okay, so this will be our first lecture on the Fourier series for ECE 343. I do recommend that you read Chapter 6 in the textbook. I won't follow it in exactly the same way that I have in previous chapters, but it does have a lot of overlap with what we'll cover in class. In the end, I'm going to derive the Fourier series in a little bit different and probably a little bit more rigorous manner than is done in the textbook. To start out, let's just see what the Fourier series is. The Fourier series is something that's attributed to Joseph Fourier. He's a mathematician and made a lot of contributions to the field of mathematics, of which the Fourier analysis is one of them. Fourier had a really big idea, and his big idea was something like this, that if you have a periodic signal, you can represent that signal as a sum of harmonically related sinusoids. We'll find there's another form of Fourier as well. In fact, there's several forms of Fourier, but for right now, we're gonna worry about the Fourier series. So let's just write this out and think about why it might be such a neat thing. So a periodic, so we're going to go ahead and start with a periodic. A periodic, we need to give it a period. So in this particular case, we're going to think of a period T naught being equal to 2 pi over some radian frequency, fundamental frequency omega naught. So a periodic signal, Fourier's big idea, a periodic signal can be represented, right? Can be represented as the following. We have that signal x of t, and we're just going to decompose it. So we're going to write this one as a summation. We're going to let that sum go on a variable, we'll call it k, going from minus infinity to infinity. So there's an infinite number of terms here. There's some coefficients. We'll call those x of k. Later we'll find those are called the Fourier series coefficients. And then we're going to get an e to the j k omega naught t. So really, what does this say? It says that any old signal, so we look at this equation, so the x of t is some t naught periodic signal. We did assume periodic here, some t naught periodic, and this is periodic continuous time signal, right? Some t naught periodic signal equals, so is, right, a sum of, well, what are the xk's? Those are just scale factors, so scaled, right? And then what are the exponentials? Well, they're just exponentials, but they do, right, have a particular frequency. They have a frequency, each component is an integer multiple of that base frequency, omega naught. So it's a sum of scaled, what we would call harmonically related exponentials. Now, we also know just through Euler's idea that e to the jk omega naught t can also be represented as what? It can be represented as cosine omega naught kt plus j sine omega naught kt. So when we say that, what Fourier's idea here, that any old T naught periodic signal can be represented as a sum of scaled harmonically related exponentials, it's equivalent to say that any old T naught periodic signal can be represented as a sum of scaled and harmonically related sinusoids. We can use the exponential version or the sinusoid version interchangeably. They both have the same kind of basic meaning in there. I'm going to favor the exponential form. It's one of the deviations I do take with the book. The book seems to favor the sinusoid, or what is called the trigonometric form of the Fourier series. I personally find the exponential form to be more elegant and simple to work with. So for the most part, as we move forward, we are going to favor what is called the exponential form of the Fourier series, which I've just drawn here. Some T naught periodic continuous time signal can be represented, it can be decomposed, right, as a sum of scaled and harmonically related complex exponentials. Okay, why is that so important? Well, part of this should be pretty obvious at this point in the class. We know that exponentials are incredibly easy as far as how they go through linear time invariant systems. If you put an everlasting exponential in, you get the same everlasting exponential out modified in gain and phase, or modified by a complex constant depending on that system function. So some maybe motivation on this, some motivation why we like some motivation, maybe you'd call it, for the Fourier series, and we'll start abbreviating the Fourier series as an FS, some motivation for the Fourier series. Why is this such an important or such a useful kind of transformation? We know that an LTIC system, so a linear time invariant continuous system, a linear time invariant continuous system, right? This linear time invariant continuous system responds to an everlasting exponential, according to a very simple, right? It's a very simple relation. This is something that we've derived previously. The idea is that we have this everlasting exponential, call it e to the j omega little t. That's our input, right? It goes into our system, right? So we have some linear time invariant continuous system going there. And what comes out is that same everlasting exponential e to the j omega t, except for now it's multiplied by that complex constant h of j omega that depended on the system transfer function or the system function cap h. And that's our output, right? So we get everlasting exponential in, same exact everlasting exponential, modified only by a complex constant. Using the Fourier series, this is a pretty restrictive case, so I would just say this is pretty restrictive by itself, right? But with the Fourier series, we can look at this. We can say, hey, any old input that you can dream of that is periodic, in this case, we'll relax that later when we talk the Fourier transform. This x of t, it's a periodic signal, can be represented as a sum, minus infinity to infinity, right, of some scaled and harmonically related, we don't really care that they're harmonically related, it just turns out to be the way it is, exponentials. And that's going to go into what our linear time invariant continuous system. What has to come out? Because it's linear, any sum of inputs comes out as the same sum of outputs. So we get summation coming on the output k equaling minus infinity to infinity. The complex constants x of k don't matter at all, right? So we still get those x of k's coming out. But how does that exponential e to the jk omega naught t come through? It just comes out as an e to the jk omega naught t times h of what? Jk omega naught, right? We've seen that. So with a Fourier series decomposition, any periodic signal, even those that aren't just pure sinusoids, right? It could be a square wave, it could be a triangle wave. We can figure out its output, right, through a sum that looks a lot like the Fourier series. And so we knew this whole sum on the right was equal to our y of t. So let's look at that just a little bit more. Y of t, right, is equal to, and it says here, a summation, k equals minus infinity to infinity. We had all of that. What I would like to do is I would like to combine a couple terms together. I'm going to write x of k together with h of jk omega naught, right? And then that's going to weight e to the jk omega naught t. Now, if I call that term out front, right? If I call that a y of k, what do I see? I see that this output expression, y of t, right, is just a Fourier-like decomposition of the signal that is our output, y of t being equal to the sum of scaled yk e to the jk omega naught t. So it's just really showing us that the output is also representable by this Fourier series decomposition. And what are the Fourier series coefficients? Well, we've seen them there too. They're just the inputs Fourier series coefficients weighted by the transfer function, multiplied, right? We've seen this kind of expression as well. We've seen before where you have something like y equaling little x convolved with h. You Laplace transform that, for example. We're going to find out Laplace transform is just a generalization of Fourier. You Laplace transform that expression x convolved with h, and you get x times h. Well, the same thing happens here with the Fourier series. We see that our output Fourier series coefficients are just going to be our input Fourier series coefficients, each weighted by the transfer function of the corresponding frequency, k omega naught. So that's a really nice and beautiful relationship. So what can we do with this Fourier series decomposition? We can really simplify how we look at input-output relationships for continuous time systems. We represent the input in terms of a really convenient set of building blocks, right? For linear time invariant systems, the building blocks that are simple are going to be these exponentials, these harmonically related exponentials in the case of an input being periodic. And then because of the beautiful properties of a system and how it acts on everlasting exponentials, we know we get a simplified output as being something very similar. It's a sum of exponential sinusoids, each weighted by their own Fourier series coefficient as well. And we can get those coefficients through a simple multiplication. So Fourier breaks things up, right, in terms of convenient building blocks, nice building blocks, if you will, for system analysis. We've seen different kind of decompositions before. Think of a Taylor series, for example. Taylor series does what? A Taylor series says that we represent a signal, right? So I could write this down as well. So we've seen other decompositions before, right? We've seen other decompositions where we build up a signal like x of t is being equal to here. How about a sum of polynomials? Right? Sum of polynomials. That was like a Taylor series. That is a convenient decomposition for certain operations like maybe integration and differentiation, where the rules of integration and differentiation acting on things like polynomials is very simple. We also saw stuff like x of t being equal to, we could have done it as a sum or an integral, so I'm going to write it as an integral, right, of some scaled and shifted deltas, right? That was the sifting property. What did we do in that case? We broke up a signal in terms of building blocks, little pieces that were delta functions. Why did we like that? Because we understood the behavior of deltas going through our system when we were doing time domain analysis. Here we're just saying that x of t, right, is going to be a sum of sinusoids, right? That's Fourier's idea. This is a Fourier kind of concept. And why is that so great? Because we know that sinusoids have beautiful and easy properties in order to go from input to an output on a system. It's going to simplify our analysis of systems. It's going to improve our intuition of what those systems do. Okay, so we have a very brief introduction. We have this idea without proof. We've only just written it that Fourier said any old continuous time periodic signal can be represented as a sum of scaled and harmonically related exponentials, right? And we have some motivation as to why such a decomposition is useful, because exponentials have convenient properties when considering linear time invariant continuous systems. For us to really understand this Fourier series, I would like to really derive it in a mathematically rigorous way, something that we were not able to do just because of the kind of prereq math requirements for the Laplace case. We did not have the complex variable theory necessary to deal with that complex differential element. Things are different here at the Fourier series. We can rigorously and completely understand both what is called the analysis and the synthesis equations of the Fourier series. We can understand this whole thing that is the Fourier series. I would like to do that in a mathematical way, but in order to do that, we need to get some background math. So I'm going to spend the next block of time, I guess, really developing some background mathematics that is going to simplify our ability to really derive in a nice way, in a mathematically complete way, in a rigorous way, this whole concept that Fourier came up with, this idea of a Fourier series. So to understand maybe deeply, right? And we would like to have deep understanding, to understand deeply the Fourier series. Okay, we need some background mathematics. Okay, I had mentioned before that I'm going to do things in a little bit different way than the book, and it is certainly a different order, but this does roughly align. It aligns with section 6.5 in the text. So if you're following along, if you read through in chapter 6, you'll definitely see the connections here. So this is all going to be about some background mathematics. Probably at the initial part, these background mathematics are not going to seem terribly relevant to signals and systems. They're not going to seem terribly obvious in how we're going to use those for Fourier analysis. I just think we need to have a little patience on this because some of the math here is non-trivial. And what I would like to do to make sure that we all have an intuitive understanding of this mathematics is I'd like to look at this mathematics in a very intuitive place, and that's the Cartesian plane. So we're going to do some math development in the Cartesian plane, something that's easy to visualize. We're going to see how things work there. Then we're going to adapt or expand those ideas into function space, so where we are dealing with functions rather than objects in a Cartesian plane. And once we do that, then we're going to be prepared for applying it all to this understanding of the Fourier series. So there's going to be some steps that we have to deal with first. So let's consider a Cartesian coordinate analogy. Okay, so I would like to look at a Cartesian coordinate analogy. I'm going to draw my Cartesian plane, so we're going to stick with a two-dimensional idea for right now. So I'm going to go ahead and draw my Cartesian plane. It has two axes. We don't have to worry too much about what those axes are for the time being. I'm going to go ahead and create or put out here an object of interest, okay? So I'm going to let this point out here, which I'm going to put a label on it. I'm going to call it x underbar. That underbar just lets us know that this is a point in the Cartesian plane. You could think of it as a vector. So I could draw a vector to that point, right? And so we are looking at a vector quantity, something that occupies a space with more than one dimension, right? We've got here the horizontal part and we've got the vertical part is one way of thinking about that. So I've got some object of interest. So I'm going to go ahead and look at x here. I'm going to say x is my object of interest, right? So we've got some object of interest. And what would I like to do? I would like to represent that object of interest using some building blocks. So in this particular case, as I'm first starting this development out, I'm going to give myself a single building block, and I'm going to make that building block be a vector that lies purely in the horizontal plane. So I'm going to go ahead and draw a little vector in here. So I'm going to have a little vector in here, and I'm going to label that vector phi. Okay. And that phi is going to be a building block. So some building block. So what do I have? I have an object of interest and I have a building block. And I would like to somehow estimate or create or approximate or build that object of interest using my building block. So my goal here, if I was going to look at a goal, my goal, right, is to estimate the object of interest, using and in this case it's going to be a linear combination. I'll put that parenthetical. A linear combo. It's going to seem like a strange linear combo because I've only got one piece right now. A linear combination of building blocks. My phis, if you will, my phis. I've only got one building block in this case. Let me give a little bit different idea, kind of an analogy to the analogy, if you will. So I'm sure many of you have had a chance to play with some building blocks back in your childhood, where you had something like wood blocks or maybe mega blocks, or you had Legos. My preference was Legos. Loved Legos, and so I'm going to use a Lego analogy here. There is a great Lego set, the Lego Death Star. If you haven't ever seen this, go out onto the online and do a Google for the Lego Death Star. It's a many thousand piece, Lego set that is meant to look like the Star Wars Death Star. Is the Lego set the true Death Star? No, it's not. It's an approximation. So we have an object of interest. These kids have got an object of interest. They like this idea of the Star Wars Death Star, a fully functional battle Death Star, the size of a small moon that can absolutely melt planets. But they have some limited resources. They have some limited pieces, and so they're only going to get an approximation. And so they're going to get an approximation that is made out of pieces, right? Out of building blocks. Those building blocks could be Legos, they could be wood blocks, they could be mega blocks, for example. But we want an approximation. So part of our goal is to find some set of blocks that make a good approximation to the object of interest, in this case, the Death Star, right? And we also would like at some point to be paying attention to what kind of building blocks we are using. So that goes back to this idea of whether it's Legos or whether it's mega blocks or whether it's old time wood blocks, something along those lines. So our goal back here again, right, is to estimate an object of interest using a linear combination of building blocks. I'm going to add something, then we'll go back up to the thing. I'm just going to say, I'm going to note, right? The building blocks matter. The building blocks matter. It's a little outside the scope of our class to spend too much on this, but we will spend a bit of it. For those of you, and so I'm just going to put down here my analogy, think of, for example, right? So as an example, think of, Lego versus mega blocks. If you were unlucky as a kid, right? You had an aunt or an uncle who sent you a birthday gift and they sent you Mega Blocks instead of Lego. Why do I say unfortunate? Because Mega Blocks, even though you could have a Mega Blocks Death Star, Mega Blocks just don't hold together as well as Legos. They don't have that same quality as Legos. They're not the quality building blocks. We would like to use quality building blocks because when you use quality building blocks, your end goal, your end objective, even though you might use the same number of pieces, is just going to be that much better. So we do need to be worried about building blocks, and we'll come back to that idea of building blocks and what make good building blocks in a bit. So back to our Cartesian coordinate analogy. I have an object of interest, call that x. I have a building block, right? Call that v. If I wanted to, I could, I guess, put also an underline on that, just kind of to emphasize its vector nature. And I want to estimate. So what do I want? I want to estimate x. So I'm going to say I want to come up with an x hat. That hat just means an estimate of. So I want to have an estimate of x that is a linear combination of my building blocks. So in this particular case, my linear combination of building blocks is just going to have a single term because I only have one building block. This is like a Lego set with a single piece available to me. And so that single piece is going to be phi. So far it seems pretty strange, but linearity includes not only the sum, it includes a scale. So I could also allow for some scale factor. So what you could think of here is that I'm going to estimate the Death Star, right? Using my single brick of Legos, that's the phi, but I can scale that brick, right, to whatever size I want. I could make a Lego that is the size of a small moon. It still might be a little 2x2 Lego, but it's going to be a moon-sized Lego, okay? And so from some measure, that is going to be a better estimate of that Death Star than the kind of Legos that you would get down at the store that are the size of your thumb. So we have this scaling parameter C, right? We have this scaling parameter C that is going to allow us to customize something about our estimate to try to get closer, to the object of interest. So let's think about what that might look like. If I scale my phi, right, that just lets it go either forward or backwards. In this particular case, the c is just some sort of real constant, right? So we can think of this c as being a real constant. That's what we'd like to think about in this particular case for this Cartesian coordinate analogy. So I have some real constant in this particular case. And so we are going to be able to scale that guy, but we can't change, right? Being where the building block, the phis, let us live. And in that case, I'm going to do this in green, right? Phi lies along the horizontal axis. And so that's where our estimate is going to live as well, because we're just scaling a piece, right, that lives along that horizontal axis. So really what we're saying is we're going to find an estimate that has to lie somewhere on that horizontal axis, what I've just shaded in green, but we want it to be as close as we possibly can to the object of interest. So let's redraw this just a little bit and consider some different cases. So I'm going to go ahead and redraw my coordinates, right? Go ahead and put those in there. I'm going to go ahead and put in my building block. So I've got my building block in there. That is my phi, right? And I have my vector or object of interest. That is my x. And what I want is I want my x hat being equal to some constant, right, scaling that vector phi. Okay, so I'm going to look at some possible cases of C. I could pick C equals -1 as an example. If I pick C equals -1, I would have -1 times phi, right? So this is a case where C equals maybe -1, something like that. And we might, just look at that and say, wow, you're definitely on the wrong track here. You're going away from that object X. Doesn't seem to make a lot of sense. I'm going to look at some positive values of C in this case then. So I could have a C that scales me out to maybe somewhere in here, and I'm going to call that C1. I'm going to have another one that maybe scales me somewhere out here. I'm going to have that be my C2. All of these guys are multiplying our phi, and I could have something way out here, maybe something like this. This would be some C3 phi, something like that. Which of these estimates, right, which of these values, C1, C2, or C3, provides the better estimate, right? Which of these is better as an estimate of that object X? We know C1 phi, right? That would be some X hat, you could call it 1. C2 phi would be some X hat 2, right? And C3 would lead, C3 times phi would lead to some X hat 3. So which estimate, X1, X2, or X3 is better? I think almost all of us would sit there and say the C2 phi seems to be the better one. And why is that? Well, we can do a real simple thing. We can look at what is the error, right? What is the error, right? The error in this particular case, if we were going to look at the error in this guy, the error is equal to x, right, minus x hat, something like that. And at least in this vector, this coordinate scheme, this Cartesian coordinate analogy or plane that we're looking at, that error, right, will have a nice physical meaning. If I take x minus x hat 1, for example, we get what? We get this piece right in here. If you take x minus x hat 2, you get this other piece, right, something like this. And if you did it again for the third one, you would get this other piece sitting in there, something like that. So this is like my error 1, this is my error 2, and this is my error 3. Which of those errors, right, which of those errors ends up having the smallest size, the smallest length in this particular case? I think length is a good measure of goodness here, right? If I had an error that was 0, that means that my estimate would be exactly equal to the thing that I was interested in. Clearly, error 2 is smallest, so we can see here, we can see that of all those 3 that I did, error 2, right, is smallest, right? Whoops, is in this particular case smallest. What do we mean by smallest, right? That means that the size of the error, right, like the norm of the error, is minimized, something like that. So here's a design criteria then for us. We want to do what? We have an object of interest, that's the X. We have a building block, we've got our Lego set, that's the phi. I want to come up with an estimate of X that is a scale value of that building block, a linear combination of that building block. That's the thing that I want. I want to make a good approximation of this object of interest. The thing that I don't know, I know what my Legos look like. I know the thing that I want. Those are known. I don't know that constant C. So I need to find a rule for finding C. A rule for finding C is to find a C that minimizes the error, right? So if I pick a C so that that end result, right, causes this error to be minimized, I've got a good design decision. And it turns out that this happens, right, when a nice relationship occurs between the error and the thing we are using to estimate our object, that we get a right angle between them. So we can see that graphically, and that principle is something that is going to be general for this kind of an estimation problem that we'll be able to utilize later. So one of the things that we might notice is that the best, right, that the best estimate, call it x hat. If you wanted to put in there best, we could do that, right? X hat best minimizes the error length, right? That's the length of that error vector, something along those lines. And that occurs, right? That occurs when the error is at right angles to our building blocks, the phi, okay? There's a different way, a little bit more mathematical way of saying that, and so I'll try to say that as well. That basically tells us that the error, right, is orthogonal to. So that upside down t is just read as orthogonal to. In a Cartesian coordinate scheme, that just means at right angles to. So the error is orthogonal to the building block. And as a result, it's also orthogonal to our estimate, which is just a scale of the building block. So our error is orthogonal to the building block. This whole thing, this leads to the best C, and therefore the best x hat. This whole idea, right? This idea is something called the orthogonality principle. So I'm going to say this is a statement. This is a statement of what is called the orthogonality principle. And we will come back to and continue to use this idea of the orthogonality principle. All right, well, let's think a little bit again about how I might get the best estimate here. I think we can probably just, instead of going back and forth, I'm going to redraw this yet again. So I would like to get a little bit more mathematical on this. So far, we've done this in a pretty intuitive kind of way. Now I'd like to get just a little bit more mathematical. So I'm going to go ahead and draw my object of interest. So I'm going to go ahead and have that guy out there. So there's going to be some vector, right? That vector is my x. That's my object of interest. I've got my building blocks. I've got my one-piece Lego set, if you will, in this particular case. That is my phi, something along those lines. And I want to find the best. We said that the best would be what? The best one would be the one that makes the error orthogonal to the data. Consider this axis a little bit different. Let the horizontal axis be like the ground, okay, and let the vertical axis just be some distance off the ground. So I've got an object, call it your Death Star, call it whatever, sitting above the ground, and I want to find the best estimate, the best approximation to that object x, where I have to be on the ground. One way to think about that is I just take that object, let's call it a ball, right? And I drop it. That ball drops down, right, to where it hits the ground. And we know how gravity works. It does it in such a way that when it drops down, it takes the shortest path. Gravity is a conserver of energy, right? So it takes the shortest path there until that ball falls to the ground. It makes a right angle. That path, right, that fell is going to be the error difference, right, between my object of interest x and this best estimate c phi. Okay, so we can get the best estimate, right, by doing a projection. We can project our object X into the plane of where our building blocks are, to where fees are. So let's think a little bit about that. Everybody should have seen in some of their math before of taking a vector X and doing what is called a dot product of that with another vector, call it phi. From mathematics, we know that we can just write that out as whatever the size of X is, so the length of X, right? And multiply that by the length of phi, and then we multiply that by the cosine of the angle between those guys. That's just a definition of the inner product, or what is also called the dot product. So I'm going to label this guy. This is the dot, sometimes called the dot or inner product between two vectors in this case. That dot or inner product is related to the distance or the lengths of each of these pieces and the cosine of the angle between them. I can write out here what the angle is. There's my angle, theta in this particular case. Okay, so we wanted to estimate X with a scale factor of our building block phi. So I know C phi is equal to my X hat, right? Now, if I take C phi and I add to it error, error is actually a vector too. It's a little vector that's going to be pointing up, if you will. One of the other things I can note here is I can note, right, that X, right, is just X hat plus whatever error there is. We can also get that as being the error is just X minus X hat, right? It's the difference between the object of interest and our estimate front. We want to be able to minimize this guy, and we've already got a sense of what does it. It's one that ends up giving us that right angle on it. Okay, so we know that the length of the component of X along the phi direction, right? The length of the component of X along the phi direction. That's what I've just drawn there for a bracket, right? The length of that component can be gotten by that projection. It can be gotten by that dot product. So we know from trigonometry, right, that thing is equal to the length of X cosine of theta, right, is going to be equal to C length of phi, something along those lines. So C phi, right, that's this piece, right? That guy's length, right, which is just going to be C. C is a positive real constant. That's just going to be the length or the size, the absolute value of C phi. That's just going to be C absolute phi is going to be equal to the length of the projection of X into the same place. Well, that's just X cosine theta. We know that from trigonometry. Okay, so now I'm going to play just a little bit game on this. I'm going to multiply this expression. I'm going to multiply by phi on each side, okay? And in that particular case, well, let's just do it by the size of phi. I'm going to multiply by the size of phi on both sides. And so that gives me something that's going to look like norm X, norm phi, right? Cosine theta, and that's going to be C norm phi times norm p is just norm phi squared, something along those lines. I can recognize now, right? I can recognize that stuff on the left. That's just the dot product. So that's just X dotted with phi. We had seen that before through our discussion of dot products. And what I can do for all of this now is I can come up with an expression for C, right? I can come up with an expression for C. C was the thing I didn't know. Everything else is known. I'm just going to solve for that C going on in there. So I'm going to come over here and I'm going to solve for C, and what I get is I get C equals X dotted with phi over the norm of phi, the size of phi squared, something along those lines. So this is a way of finding that coefficient by using this idea, this principle of how we can get a good estimate by making the error orthogonal to the data, making it have no overlapping content, having no overlapping information. They are not in any way alike one another. We find the best estimate to our object x by making the error not explained at all by anything that is in our building set, right? If there was anything in our building set that could explain part of that error, we'll then use it to explain that part of the error to reduce the error. Our best one is going to be the one where all the pieces of our building blocks are being used so that they don't have anything in common with that error. And we can find those pieces, that coefficient, at least for this first order case, this one where we just have a single building block, as a projection of x onto phi. We could do that with a dot product, and then we have to divide by the size of our building block squared. Okay, so what are we going to do? I'm going to re-clean this up a little bit. Our coefficient c, right, is x dotted with phi, right? That's an inner product. And we're dividing that by the norm of phi square. That's the norm squared. Of our building block. And I will make just a little side note on this. I would say that good building blocks, good blocks might have, right, the size of the block being equal to 1. Why? Because then you wouldn't have to do that division. You would just end up getting your size needed for each of these pieces by projecting the x onto the building block itself. The phi squared would be equal to 1. Okay, so we have a rule then for finding our coefficient. We will try to summarize these all up as well. One other thing that we might do is we might just take a look at, let's look at that norm phi squared, okay? We can look at this as actually a projection of something on itself. If I've got a building block, right, there's my phi, and I look at a projection of that onto itself, that would be what? That's going to be the length of phi times the length of phi times the cosine of the angle between them, but because it's phi with itself, the angle is 0, and the cosine of the angle is equal to 1. So phi squared could be thought of as norm phi times norm phi, right? Cosine of 0, whoops, let's make that a 0, not a theta. The theta is 0, cosine of 0 in there, right? Which is just phi dotted with phi. So I can get that bottom also with an inner product. It's just a projection of something on itself, something along those lines. So we can do all of this stuff through these inner products, or what you might have more commonly heard of as a dot product. Okay. Okay. So last pieces in here. We should have a couple final notes on at least this part, some notes, and then we'll do some summaries on this. If x dotted with phi is equal to 0, and it doesn't have to be these, it's just any two things with a dot product equaling to 0, we say the vectors are orthogonal. And we'll use that little orthogonal symbol. So if we had x dotted with phi equaling to 0, we would say x is orthogonal to phi, right? These are equivalent kinds of statements. That orthogonality means that they don't have anything sort of in common. They don't share any underlying information. So that's one of them. To get the best, right? To get the best estimate x hat. And what does the best estimate mean? We need a value c, right? We want the error to be orthogonal to our building blocks, e orthogonal to phi. That, again, is the orthogonality principle. It's the way we can get the best measured as minimizing the length, minimizing the size of the error. So let's go back again to our picture. And I'm going to do a very quick summary. I have an object of interest, x. I have a building block, phi. I want to estimate, right, the object of interest, that's x hat, as a linear combination of my building blocks, which in this case is just a single building block, phi, right, scaled by some unknown value, c. I know my building blocks. I know the thing of interest. The best here is going to be the one that minimizes the length of the error. So I have my error here, right? It's the difference between x and x hat, and I want to make the length of that guy small. We had seen before that the thing that makes that small is by making it at right angles to where our building blocks live, right? That those guys have to be at right angles. That's the orthogonality principle. The best estimate, the best C, the way we want to choose our C's are the ones that make the error orthogonal to the data. Now, when we had that condition met, we got this right triangle, right? That was this triangle right here. And we started writing the relationships that we could get from that right triangle. And we found that that required us to have C, right? C, right? If I did that in here, in this particular case, it told me that my C had to satisfy something that the value C could be gotten, if you will, by the projection of x onto phi, right, divided by phi squared, something along those lines. Okay, so let's do an example that actually has some numbers in it. We're going to do an example with some numbers and see if any of this kind of holds true and holds out. So I'm going to go ahead, continue. This is still going to be a Cartesian coordinate example. In this particular case, I'm going to go ahead and I'm going to have 1, 2, 3, and then 1, 2, something like that. So I have a horizontal and vertical axis. I'm going to choose in this particular case going up 1 in the horizontal, and I'm going to come over 3 in the no, I think I said that wrong. 3 in the horizontal and 1 in the vertical. That is going to be my object x, something like that. So I'm going to go ahead and draw that. I'm going to draw that vector in there. So I've got a vector x, right, which you could think as a coordinate pair as a 3, 1, right? 3 in the horizontal, 1 in the vertical. But I'm going to just go ahead and draw it as that vector. Stretches over 3 in the horizontal, goes up 1 in the vertical. I would like to estimate this guy using a building block. My building block I'm going to use here is going to be constrained to live in the horizontal axis, but I'm going to make it a little non-standard than maybe what you might have seen with some of these things. I'm going to make my building block phi be a point that is 2 units over in the horizontal. So you could think of phi as being this idea of 2 in the horizontal, 0 in the vertical, right? So it's constrained to live in the horizontal axis, something along those lines. What do I want? I want, right, the best, right? I want the best estimate. I want the best estimate. I want the best estimate x hat that has the form c times phi. Now I know what phi is. Phi is just a 2-length vector in the horizontal axis. I know what x is. It's the point 3, 1. And I want to find the best estimate as a scaled version of phi. We already know what that looks like. We know that that best estimate is going to put us over here, right, directly underneath x, just like if x were some distance 1 above the ground and we dropped the ball, it would fall down at that location 3, right? So we know here that that best, that x hat, if you will, right, is going to be equal to that 3 by 0. That's what it should be. So something scaling 2 by 0 has to be equal to 3. Well, we already know what the c should be. The c should be equal to 3/2. I just want to make sure that the math works out. So I know the estimate here should be 3, 0, which should be some c, right, phi, which in this case had better be 3/2, right, times phi, which would then give me this 3, 0. We can see that graphically. That's the one that's going to cause those guys to be at right angles. That's the one that's going to give me the best. Let's make sure that the math that we got works out. The math that we got says that the orthogonality principle tells us what is best. The orthogonality principle will give us an error, E, that is minimized, right, by projecting X down onto the phi, that's through a dot product, and then dividing by the size of phi squared. So according to the orthogonality principle says what? The orthogonality principle says our best. So minimize the error, minimize the size of that error, right? Our best estimate is found, right? We just derived this as being C equaling X dotted with phi, right? Over phi sized squared, which we said we could do through an inner product as well. Okay, so in this particular case, what is X dotted with phi? X dotted with phi, right, in this particular case, is going to be equal to the size of X, right, times the size of phi times the cosine of the angle between them. So if I go back up into this, right, I need the length of X, that's this thing, right? I need the length of phi, that's this one, and I need something about the angle between them. If you use your trigonometry here, we can find out a few things. A few things that we can find out is that phi is going to be equal to, in this particular case, is being about 18.4 degrees. We know that the size X is equal to what? It's the square root of 3 squared plus 1 squared, the horizontal and the vertical each squared and square rooted. That's just trigonometry, so that's going to be root 10. The size of phi, right, is just going to be equal to, well, I could also do that as a 2 squared plus 0 squared. Well, that's just going to give me 2, something along those lines. So if I go back up to my expression, X, right, dotted with phi is going to be equal to root 10 times 2 times the cosine of 18.4 degrees. And if you do that more accurately and carry that out on your calculator, what you get on this is a value of 6. I'll leave that as a calculator operation for you to do. Root 10 times 2 times the cosine of 18.4 degrees, at least as close as I can get with one decimal point, will come out and give you a value of 6. It is actually an exact value of 6. What is phi, right, dotted with phi? What is the size of my building block squared? Well, I had already seen the size of phi, right? The size of phi we'd seen before, we'd already calculated that out as being 2. So we know that this is norm phi times the cosine of the angle between phi and itself. Well, that's just cosine of 0. So that's going to be equal to what? It's going to be equal to 2 times the cosine of 0 is going to be 1. That's going to be 4. All right, now we're ready to go. Our best coefficient, the thing that gives me the very best scale factor, so that my x hat, which is just a scale of that building block, c times phi, that scale factor c is equal to the projection, right, that dot product x dot phi, right, divided by the phi squared, which is phi dot phi. We computed the numerator in this part as being 6. The denominator we computed as being 4. That is 1.5 or 3 halves, however you want to do it. 3 halves times 2 absolutely brings me back where I wanted to be, right? It brings me right here to that point, which is that projection point that causes the error to be orthogonal to the data. It is the best, the one that minimizes the length of the error, being constrained to be in, that area of the space where our building blocks are at. Okay, well, we can expand this just a little bit. I think we've hit some of the main stuff. We've used a Cartesian-coordinate analogy to show that when we have an object of interest and we've got building blocks, we know how to find the best linear combination of those building blocks, at least when we only have one building block. And we use something called the orthogonality principle, right, to help us find the best. We can make the error the smallest, right, as long as the error is orthogonal to the data. So we project our object x down into whatever holds our building blocks, right? And then we do a little normalization based on the size of our building blocks squared. Well, let's look or expand this just a little bit beyond just having one Lego. One Lego sets are pretty boring, so I'm going to try to do something that's going to give us two Lego pieces. This is not the easiest thing to draw, so you'll have to use a little bit of imagination here. But what I'm going to do now is I'm going to, instead of have a Cartesian plane, I'm going to talk three space. So I'm going to have a three-dimensional space. I'm just adding another dimension in there. And so I've got some object of interest in there. I've got some vector going to some object of interest. That's my x. That's a vector sitting out there in three space. I'm going to have some building blocks in here, right? I'm going to have some things that I'm going to try to estimate my x with. So maybe I have one that's aligned along this bottom plane, right? This horizontal axis, and I'm going to go ahead and call that guy my phi1, okay? And I'm going to go ahead and let myself have another vector, and I'm going to call that guy phi2. And for this particular case, I'm going to show those along the horizontal, and then the other, I guess you could call it horizontal, the things that make a flat plane. Phi1 and phi2 just give us a Cartesian plane. X is somewhere above that Cartesian plane. It has that vertical part. It has that axis that goes along the vertical axis as well, okay? And I want to estimate X with some X hat that's made up of just my, not one now, but two building blocks. So I want an X hat as being some C1, phi1, right? Plus some C2, phi2. I need to find not phi, I need to find C's, both C1 and C2, the things that scale phi1 and phi2, that minimizes the error of the difference. Well, everything here is going to be the same. Our error, right, is going to be equal to x minus x hat. It's just the difference between my estimate and the thing that I'm interested in. We are going to do this with a projection. We are going to project x into the phi1, phi2 plane, if you will. So if you thought of x as being a ball, right, and it's above some flat plane, right? So I'm holding a ball above the earth, and I drop that ball. That dropped ball, right, is going to eventually hit the plane sitting in there, right? And when it hits that plane, right, that is going to be, that's my projection. That is going to be my x hat, something along those lines. What does that x hat look like? Well, it's got a component that's in the phi2 direction. It's also got a component that's in the phi1 direction, something along those lines. This is where drawing on a flat piece of paper when you're trying to do three spaces is a little bit difficult, but hopefully it's starting to come together. So my x hat there is what? It's equal to some C phi1, right? That C phi1, right, is going to be this piece right there. That was this C phi1. And then I'm going to go some C2 phi2, right? And so that could be like this piece. So I'm going to have some, well, that first one should have been a C1. So I'm going to have some C2 phi2, right? And I've gone ahead and drawn that in blue. And then the combined combination of those guys, right? That is going to be my x hat. That gives me this last piece in here, right? That shows me where I get to. I get to that point, which is the projection. It's where that ball fell when I dropped it. Well, a couple things that we can notice in here, if we use our creativity a little bit, right? One of the things that I'm going to notice is that, let me do this in red actually. I'm going to notice that this dotted path that I showed when I dropped the ball, I'm going to do that in a dark red line, right? What is that equal to? Well, that's just my error, right? That's just x minus x hat. So I've got my error there. And I know that that error is smallest. Gravity is a stingy one. It takes the shortest path to get us to the Earth. It wants to save as much as possible as far as effort. And when I take a look at that error, right, and I compare it to things like the phi1 and phi2, I notice a few things. I notice that it's at right angles, right? So there, my error is at right angles to phi1, and it's also at right angles to phi2. Orthogonality principle here works. It's exactly what we'd expect. The one that gives me the best estimate, the best x hat, the linear combination of those, the C1 and the C2 that give me the best ones, right, are going to be ones that cause the error to be orthogonal, right, to all of the pieces, both the phi1 and the phi2. Okay, so I'm going to just go ahead and summarize that here. So we know that the best x hat, right, has the error, right, orthogonal to the phi1, and it has the error orthogonal to the phi2. Okay, so the error has to be orthogonal to the building blocks. These two guys are both statements of the orthogonality principle. The orthogonality principle says we can find those best coefficients, right, by making sure the error is orthogonal to the data. I'm going to have to do a little bit of hand waving on this part, but I will just say since phi1 is orthogonal to phi2, didn't have to be that way. It's just good basis function. So I'm going to say this is a good building block. Good building block. This is a good building block property that I'm going to write out here. So let me try to get this done right. This is a good building block property. A good building block property. You know, another term for building blocks, and I probably have already said it a couple times. I don't know if I've introduced it formally. Mathematicians have a better name for this, or they use a different name for this. Building blocks are kind of an intuitive one, but mathematics would call these guys basis functions. Okay, so our building blocks are what are called basis functions. Basis functions are just the basis for the space that we're living in. They're the fundamental building blocks for our space. So since our two building blocks are orthogonal to one another, this is a great property. Since we have that, since this, then we know something else, and this is something we'll derive in detail better, that I can find any of those individual coefficients as being what? It's just x dotted with that particular basis function's coefficient that I'm looking for, right? That basis function phi over the size of that particular basis function squared, which we could get as an x dotted phi over phi dotted phi. This is exactly what we saw for the case when we only had one building block. Here, if I have two building blocks, I can get each of those coefficients individually, right? Because the building blocks themselves are orthogonal. We will take a look at a later lecture of a case when the building blocks are not orthogonal and why things might look a little bit different from that. Okay, so let's go back here and just make a quick look at this. We were trying to build some mathematics that are going to help us in the Fourier series. Probably a little hard to see that right now, but this first set of mathematics that we're trying to illustrate is meant to help us illustrate a principle called the orthogonality principle. The orthogonality principle comes into play when we are trying to estimate an object of interest using some building blocks. It says that the best estimate, the one that minimizes the size of the error, is one that causes the error to be orthogonal to the data. This most recent case, this one here that I've done in the 3D space, is allowing me to have more than one building block. So I've got two building blocks in this particular case. So my estimate here, right? If I looked at my estimate, it's a linear combination of my two building blocks. I know what the building blocks are. The only thing I didn't know were the size of each scale factor multiplying those building blocks. Orthogonality principle comes in and tells us how to find those C's. We want to project x down into the phi1, phi2 plane, and that, when we do it, ensures that the error is orthogonal to both phi1 and it's also orthogonal to phi2. If phi1 and phi2 are orthogonal to each other, we can find those coefficients of interest just by projecting x individually onto phi1 or phi2, dividing by the size of either phi1 or phi2 squared, something along those lines. Okay, so I think we've laid out the basic Cartesian coordinate analogy. We've done a little bit of examples on this guy. We've illustrated or introduced a fundamental principle to this estimation problem. That's the orthogonality principle. And what we need to do next is we need to think about how we can apply this not to things in the Cartesian plane, but how we can apply this to the things we're interested in a signals and systems class, which is signals. I would like to be able to do this in terms of not points in a plane, but in terms of signals. And so we're going to have to do a little bit more work to apply this to signals and make sure that we can apply these concepts in that case. That will be next lecture.